So when you do this, so what can you do this way? What kind of false memories can you imprint onto a collective agent? And let's just take stock of what we've said so far. Groups of cells are a collective intelligence which navigates anatomical space to solve various problems and reach the correct region. So what happens when we incept false memories into this collective agent that is storing and processing those memories in an electrical network? Well, one thing you can easily do is inject a particular ion channel RNA to trigger a voltage state that corresponds to that eye spot that I just showed you in that electric face model. And when you do that, let's say we do that to a bunch of cells that are going to become gut, those cells become convinced to make an eye. And so here's a tadpole, here's the gut, here's the eye sitting on their gut. You can make eyes anywhere, in fact. So this, and these eyes, if you section them, they have all the right lens, right, and the optic nerve, all that stuff. So there's a couple of things you learn from this. One is that the bioelectric pattern is instructive. It's not just about making errors or causing monsters. It's about telling the cells you should build an eye, and they actually build a complete complex structure. Number two, this is hugely modular. We have no idea how to micromanage the formation of an eye. It's very complex. What we do know is how to put in a memory that's basically it's a subroutine call or a trigger that says build an eye here. All the competency is in the rest of the cells. We just found the language by which they encode which structure should be built, right? And downstream of that is all of the correct gene expression, all the size control, all of that stuff is downstream. There's also another really cool aspect to this, which is this. This here is a cross section of a lens sitting in the tail of a tadpole somewhere, and the blue cells are the ones that we actually injected with our ion channel. So the blue cells have had their voltage modified. All of these other cells are completely natural cells, but they all participate in this lens formation. Why? Because these cells can ascertain that there's not enough of them to build a whole lens. And so they recruit their neighbors. And so much like other collective intelligences like ants and termites, which recruit their buddies when something needs to be done and there needs to be more of them, this collective intelligence scales to the task at hand. Again, natively, we didn't have to teach them how to implement this or try to micromanage it in any way. And in fact, there's actually a really interesting battle going on here, because what you can do is you can make any number of these blues. This is also frog embryo, and these blue spots are other areas where we've injected our potassium channel. And what they're doing is they're expressing eye precursor markers. But in the end, they might only make one eye, not the three that you might expect from looking at this. It's because the cells are fighting it out. The injected cells are saying to their neighbors, "Hey, let's all make an eye. There should be an eye here, and you guys need to help." The surrounding skin cells are saying, "No, you should be skinned. There doesn't need to be an eye here. You should be skinned." And depending on how that conversation goes, you might make 0, 1, 2, or more eyes. So this is a very much a collective intelligence kind of problem where they're actually communicating with each other to decide what's going to happen.